Hello and welcome again to lectures on state space approach to control system analysis and design. In this week, we are discussing the case study of a nuclear reactor. In the last lecture, we considered the development of a nonlinear model. Now in this lecture, the topic of our learning and the investigation is the linearized model. So straight away we go to what we did in the last lecture. As you saw, we derived the nonlinear mathematical model, and we saw that the control rod has to be at the zero position, and thereby the neutron density will be constant. So that is the equilibrium condition which we considered. Then we saw the stability characteristic of the system. It has two eigenvalues at the origin, so unstable. And then we simulated it for a representative transient. We introduced a disturbance at the input terminals, and we saw how the system behaves. Now in this lecture, we linearize the nonlinear model, and then we arrange the equations so obtained in the standard state space form. We will investigate the various properties like stability, controllability, and observability of the system. And we will also see the transient behavior of the linear system. We will obtain and we will compare the response to that obtained through nonlinear model, just to see the extent to which the linear model represents the nuclear reactor. So proceeding ahead, a recap of what we did in the last lecture. So we derived these 5 differential equations, 2 algebraic equations, and we gave the parameters. Now we derive the steady state behavior of the nuclear reactor. Now the steady state of any system is the one in which these various derivatives will become 0. So d eta by dt should be 0. Similarly, d psi by dt should be equal to 0, and so on. All these various variables should be 0 at equilibrium. And considering that, we derive the steady state condition of operation of a nuclear reactor. So let us see the first equation, which is d eta by dt equal to k rho into h minus beta divided by L star into eta plus lambda into psi. This is the equation. Let me just verify. Yeah. So purposely I have not shown the argument t, which is appearing along with the variables. Now if this has to be 0, then we also add 0 with various variables. So we'll see that k rho h0 n0 by L star minus beta n0, sorry, this is eta 0, beta eta 0 by L star plus lambda psi 0 equal to 0. This is what it leads to. Now if we consider the second equation, which is for delayed neutron precursors, d psi by dt equal to beta by L star into eta minus lambda psi. Again, if it has to be at steady state, then this should be 0 and the variables will be this. Now we see that beta eta 0 by L star and lambda psi 0, they balance each other. So this one says that this and this will cancel, and what we get is k rho h0 eta 0 equal to 0. Now this is satisfied in two ways. One is H0 equal to 0 and other is eta 0 equal to 0. This condition is not meaningful because nuclear reactor has to operate on power. So neutron density equal to 0 is not something for which the nuclear reactor is designed. It has to be greater than 0, which can actually be met is this, that the control rod can be kept at the equilibrium position H0 equal to 0. That means mid position, which I discussed, which I told in the preceding lecture. So the steady state of reactor is achieved when eta is eta 0 and that should match eta D, which is called as the demand. So reactor power has to match to demand. At that time this psi 0 will be, it came from the other relation, this relation, psi 0 will be beta by L star eta 0. So it is this one. Then similarly from other equations we'll have Vn0, Vn0 will be Kn eta 0, Vr0 will be 0 and Vr bar will be this much. One can derive the first one and the second one I have done. From the first one all these follow. So a reactor is at a steady state means neutron density is constant equal to eta 0, which matches with the demand power. The delayed neutron precursor concentration is constant at a value given by eta 0, proportional to eta 0, the corresponding value. The voltage of the linear amplifier is constant, again given by eta 0, corresponding to the eta 0, the power at which the reactor is operating, or the neutron density which is there in the reactor. Rate of change of neutron density should be 0, so this is 0 and reactivity in the system should be 0, and therefore the control rod equilibrium, control rod should be at its position corresponding to the critical reactor. Critical reactor is one in which the neutron flux at one time instant is same as at the preceding time instant and so on. So this is the nuclear reactor at a steady state. Now around the steady state we consider small changes and linearize the system. So again what we will do is that we have d eta by dt equal to k rho h by L star minus beta into eta plus lambda c. This is the equation for neutron density. We consider eta equal to eta 0 plus delta eta, and this is psi, and psi equal to psi 0 plus delta psi. We make these substitutions in this, and so we will have d n0 plus delta eta, eta 0 plus delta eta divided by dt equal to k rho h0 plus delta h minus beta divided by L star into eta 0 plus delta eta plus lambda into psi 0 plus delta psi. Now if you open these expressions, then we will get term k rho h0 eta 0 and lambda psi 0, and k rho h0 delta n, beta n0 beta delta n, and delta h delta eta, sorry delta n I'll end up calling that is delta eta. So what we do is we ignore the product terms delta h delta eta, and then we find that k rho h0 minus beta into n0 plus lambda psi 0, that is the steady state condition. So those terms will vanish. So what remains is k rho eta 0 divided by L star into delta H minus beta by L star into eta 0 plus lambda into beta by L star into delta eta and minus plus lambda delta psi. The first equation gives this. Similarly, we can do similar substitutions in other equations and we can derive the linear equations corresponding to the nonlinear model. And that leads to this set of equations, the 5 linear equations corresponding to the 5 differential equations. And the 2 output equations, that reactivity equation, rho was k rho into h, that yields this, and Vr was Vr bar plus Kr by tau r into Vn, that leads to this. So we have linearized differential equations and linearized those algebraic equations. Now we identify the state vector like this. The first state is neutron density, change in neutron density. Second state is change in delayed neutron precursor concentration. The third state is change in the voltage of the linear amplifier. Next one is that intermediate variable depending upon the rate signal, and the last one is the change in control rod position. So if we arrange the state variables like this, outputs are the two voltages, the linear amplifier voltage and the linear rate voltage, and input is of course the change in voltage to the control rod drive. So if we have this state, this output and this input, the system is represented like this. This is the state equation and this is the corresponding output equation. In these, A and B are respectively like this. You can, looking at the terms, you can arrange those coefficients in the matrix form, and so we get x dot equal to ax plus bu, y equal to cx, the representation of system by this linear model in which A, B and C matrices are given like this. This is the linear model in the state space standard form. Now if we solve for the eigenvalues of this, when we substitute the various values, beta, L star, lambda, they were given. So when we substitute and obtain the eigenvalues of A, we will get these eigenvalues. In the S plane, 2 at the origin, this is sigma and this is j omega. 2 at the origin, one very close to origin at minus 0.5, one fairly away at minus 10, and one very far away at minus 650. This is what we obtain, the 5 eigenvalues for the system. And this is the table reproduced from that nonlinear model. If you see at the equilibrium condition, critical condition of the reactor, then the eigenvalues of nonlinear system when H is 0, those and these, they are exactly the same. One thing. Now we look at the properties, controllability and observability. First, we state the result straight away. The linear state space description of the nuclear reactor is controllable if eta 0, that means the power of operation of the reactor, actually we'll see it will come eta 0 not equal to 0, but because we are not considering that negative, power cannot be negative, so eta 0 less than 0, that is not admissible, and the condition comes eta 0 not equal to 0, so together they give eta 0 greater than 0. When this is satisfied, then the linear model is controllable. Also, the same condition governs the observability of the system. So the system is controllable and observable if eta 0 is greater than 0. Now we derive. So first we consider the controllability. So for this we reorder the system. In that description, delta eta was the first stage, this was the second stage, this was the third, this was fourth, and this was fifth state. However, we are rearranging them, and after the rearrangement, the system matrix changes like this. From where we can actually argue the controllability. So this is the transformed system we get when we reorder the state variables. This is the system matrix when the variables are reordered, and from this we will conclude controllability in a very, very simple way by just considering the partition of the state variables like this. Now what you see that the variation of the control rod position, the speed doesn't depend on any state, it only depends on the applied voltage Km times V. This is the first observation we make. So this is that observation. The second thing now from the remaining state variables is that because the input is directly reaching that, so that state is controllable. That is the first thing. Now the system will be controllable if this remaining fourth order system characterized by this A matrix and this B matrix is controllable, then the system will be controllable. Now how we argue the controllability of this system? So that is in the next one. That system can be thought of broken like this, two second order systems like this. One is containing this, here it is 0, please see. This group of states doesn't depend on those, and it contains the input like this. Now this should be controllable and this should be controllable, then the overall fourth order system will be controllable. So that is stated in these bullets. So in fact it is stated that this is controllable, this because this is a triangular system, and this considered as a input matrix, this reaches here, and then this is triangular, so it is controllable. Or you can check by assembling the controllability matrix to convince yourself fully. And this is controllable if this term is non-zero, and this term will be non-zero because k rho is non-zero and L star is non-zero, so it will be non-zero only if eta 0 is non-zero. And non-zero means we don't want negative power of the reactor, so eta 0 should be greater than 0, then this subsystem is controllable. This subsystem is already controllable, so this subsystem is controllable, and delta H, that state is controllable, so the overall system is controllable. This gives the proof of controllability. Now we consider observability. Now again we reorder the state variables in the form from which we can argue the observability. So this is the A matrix, this is the B matrix, and this is the corresponding C matrix. So we call this as A hat, we call this as B hat, and we call this matrix as C hat. So now the new description of the system after reordering of the state variables in this is given by A hat, B hat, and C hat, and of course observability comes through A hat and C hat. And in order to argue better, comfortably, generally we are more comfortable with arguments of controllability. So we know that observability of a linear system is equivalent to the controllability of the transpose. So we will consider A hat transpose and C has transpose, that pair, and this is the A hat transpose, this is the C hat transpose. We partition it into one third order and one second order system. Now you see this part of the matrix C hat transpose, this is of rank 2. So input matrix for this subsystem has rank 2 and this is a second order system. So this part is controllable. This part of, so that means F2 to H2 is straight away controllable. And this will be, this is 0, we need not consider that. This needs to be shown as controllable. Then what will happen? The overall system A hat transpose, C hat transpose will be controllable. So we'll see in the next slide, that is also shown. So we noted this F2 to H2 is controllable, and so F11, F12 has to be controllable, and this is its that B, A, B and A square B matrix. So what we have done is, this is F11, this is F12. We take this column, 0 column we need not consider, and we are assembling F12, F11, F12 product and F11 square, F12 product. There is another way, in fact, so that will again require reordering, and we can see something like this, that this is here and this part is for this one. So F11, F12 is controllable either by assembling this matrix. This is F12, this is F11, F12, and this is F11 square, F12. And it has indeed rank 3 if this eta 0 is not 0. And because it cannot be negative, so its rank equal to 3 if eta 0 is greater than 0. Now when we combine all this, we see that the system is controllable, system represented by this is controllable, and so the system represented by AC is observable, and this is the condition. So thereby we have proved the controllability and the observability of the system. Now if we try to prove the observability through the test of rank of observability matrix, so if we assemble considering only the first output, we will get this observability matrix, this one, and in this column is 0, meaning that its rank is less than 5, and so the system is not observable by one output, that linear voltage output. We consider the second output and we again assemble the observability matrix like this, and we see that rank of this matrix is less than 5. When we evaluate, we will find that essentially due to the numerical errors, it is less than 5, not necessarily numerical errors, it comes less than 5. So the system is not observable with one output, not observable with the second output. Together, what is the situation? If we assemble consider the whole C matrix and assemble the observability matrix, means all the 10 columns, 5 columns from first output, 5 columns from the second output, we still find that rank is less than 5, and this is because of the numerical errors, because we have analytically proved observability. So you saw here some numbers are very large and other numbers are 0, so that condition number of the matrix is very poor. The same happens when we consider the full observability matrix of all the 10 columns, and so it is computational error. Even though we have proved observability analytically, through computations it shows rank less than 5. We have to take care like this when we actually handle physical systems. How does observability criterion leads to better handling? So we have these eigenvalues, 3 in the left half plane and 2 at the origin. So one by one we can check the rank of this matrix, which is the Hautas criterion, lambda I minus a c. So this eigenvalue is observable. We repeat the test for other eigenvalues, second one, third one, and fourth, fifth, and we find that all the eigenvalues are observable for the whole C matrix. If we consider for output 1 and output 2 separately through Hautas criterion, we find that this eigenvalue is not observable by first output, and these eigenvalues at origin are not observable by the second output. And this is what was analytically coming, that system is not observable by any one of the outputs alone. Both the outputs only make the system observable for eta 0 greater than 0. So what we see that for this system, the algebraic controllability test criterion doesn't conclude controllability properly. However, the Hautas test criterion leads to correct conclusion about observability. Controllability criterion is shown by algebraic test. There the yield conditioning is not that severe to hamper the controllability test based upon the rank of the observability test matrix. Now we investigate the transient response of the system, and we consider two transients, and of course we will compare the transient response of linear system with the transient response of the nonlinear system in both the transients. So the system is initially at steady state. Input is changed to 10 volts for 1 second, and then it is brought back to 0. Subsequently it is 0. So just this much change. What will happen, because input has been changed and because dH by dt is V, d delta H by dt is delta V. So because of this voltage change, this control rod will move at a constant speed during this period of 1 second, and thereafter it will stay at that new position. It was at 0 position, however it will go to a new position and then it will stay there. So let us see what are the various plots. So this is that voltage signal as I described. It is taken to 10 volt for 1 second and then made 0 subsequently. This is that control rod position. As long as the voltage was 10, this slope is 10, so it goes to a new position. its slope is km, which was 004. So km into 004 gives 04. It goes to that position and it stays there. And we have seen that reactivity rho is k rho times delta H RH. So it is positive reactivity into the system, and thereby the neutron density should rise. It indeed does. This is the change in neutron density with respect to equilibrium value of 1. Initially, when the control rod is moving, it starts rising, and subsequently it rises by a constant rate as shown by the linear. However, this will be exponential for nonlinear. If detailed plot is made for longer time, this nonlinear graph will show exponentially rising. However, linear will just rise with time, proportional to time. So this gap will increase as the time goes. You can see the gap is smaller in this portion and it is large in this portion. It will become, so if we see after long time, this is the nonlinear and this way it will be linear. However, in a small time of the order of a few seconds, this difference is very small. At the end of 10 seconds, you can see this has gone to somewhere midpoint of 0 to 5 and 0 3. So 0 to 5 5, 0 to 5 7 5, and this is only slightly below that. So we can say that for small scale transients or for large scale transients, this is large scale transient for a small time. For such a transient, the linear model predicts results close to the result predicted by nonlinear model looking at the delta eta. Now if you look at delta Vn, the same thing. If we look at delta Vr, the same thing. So delta Vr can be predicted, delta Vn can be predicted with sufficient accuracy by linear system. That is the conclusion from the first transient. We consider the second transient. Now again the system is at steady state at initial t equal to 0. The waveform of input is now different. It is changed to 0.5 volt, kept there for 10 seconds, then dropped to minus 0.5 volt, kept there for another 10 seconds. So entire transient duration is 20 seconds. So it is positive pulse followed by a negative pulse, both of the same magnitude, plus 0.5 volt and this side minus 0.5. So in this situation, as we see, this is the input signal. This area and this area are exactly equal. Now what happens when the input signal, that voltage is positive, the control rod is traveling out at a constant speed corresponding to that voltage. Then it reaches 2% change from the equilibrium. And then when the voltage is made negative, when it is made negative after 10 seconds till 20 seconds, the control rod starts traveling at the same speed inside the core and it reaches the equilibrium at the end of the next 10 seconds. Of course, we have not considered any time constant with the control rod. We have assumed its drive is instantaneous, and so this change is instantaneous. So in the essence, the control rod is moved out by 2% and then brought back to 0. This is the transient because of that disturbance voltage. And during that, this is how the neutron density has deviated from its equilibrium value. It deviated, and this is the time when control rod came to its equilibrium position. However, neutron density doesn't reach the equilibrium position. This is a typical characteristic of a nuclear reactor. So in order to nullify fully the negative reactivity should have matched. But because this control rod was not taken on the negative side, so neutron density stabilizes when the control rod reaches the equilibrium. However, it stabilizes at a different value and not at the same equilibrium. As we saw from the steady state equation, this eta 0 h0 equal to 0 is the equilibrium condition, and this can be satisfied for any eta 0 not equal to 0. So it is satisfied here, it is also satisfied here, that we see. This is the neutron density, which is essentially a replica of that, except for the small time constant which the voltage has, that creates a little smoothing at these points. This is the rate. So what we see is from all these plots that linear and the non-linear both predict identical results. So the linear model is producing results similar to the non-linear model, that is even established by transient 2. So both from transient 1 and transient 2, this is established. Now summarizing the lecture, we find that linear model shows stability characteristics similar to that shown by the non-linear model, and then from the transient response we evidenced that the time variation of all the different variables is identical to that obtained from the non-linear model and the linear model. Linear model predicts results as very close to what non-linear model predicted, slightly small but very close. So it means that this linear model can be used for design purposes and for small deviations from equilibrium for analysis purposes also. Other thing we did is we have proved controllability and observability of the system analytically. Now, so far from the linear system, we find that system is unstable. It represents the nonlinear model characteristics, so it can be used for design, and it establishes the controllability and observability of the system, means that we can design a controller for the reactor to stabilize it or to obtain good response. And because it is observable, means we can also design observer and estimator for the reactor, or some other form of controllers like multi-rate output control, fast output sampling control, or periodic output feedback control. This gives a promise that all forms of controllers and observers can be designed. So thank you very much. We will take in the subsequent lecture the design. Thank you.